So thanks everybody for coming. So I talked mostly yesterday about science. I also spend a lot of my time developing numerical algorithms for orbit integrations. I've worked a lot on the REBOUND N-body package with Hanno Rein, who's at the University of Toronto. And I don't know, for the last decade or so, it's become a pretty popular tool for doing N-body integrations, mostly planetary, but people also use it for some stellar and galactic dynamics. So my plan was to start there and I don't know, maybe leave it a little bit open-ended, depending on people's interests. So I was hoping to start by asking, well, like, are people more on the planetary or galactic dynamics side by a show of hands? Like, who would do more planetary? Okay. And then galactic dynamics. We have that. Okay. Perfect. I'm hoping to also make some of this a little bit of choose your own adventure. I'll sort of give a broad introduction and then give people a couple options on things that they could try out. How many people have used REBOUND before?
Long time ago.
Okay. Okay, so that's a good place. That's a good place to start. So how many people have used an N-body integrator before? Okay, so a lot of different, I think one thing that is a little bit different about REBOUND that is really nice is that a lot of codes will have some sort of input file that has some format. You like put in all the parameters that you want to use, you let it run, and then it gives you some sort of output file. REBOUND is organized a little bit differently in that it takes a somewhat more modern approach of giving you an API, which you can think of as a programming language for doing N-body type integrations. So it's a set of functions where you write your own code to do the things that you want to do. And I think that's a really powerful framework because in the situation where you have an input file, when you want to do something different, you have to go into somebody's code and figure out what you need to change to do the thing that you want to do, which means that people end up with all different versions of the code. Whereas with REBOUND, everybody's trying to do different science. We just give you the tools to do whatever you want. And then there's one central repository that has all the functions, which we can keep updating and fixing things, and everybody shares the same code base. So I wanted to start with this Jupyter notebook, which I put together for a course that I taught. So if you, like on your laptop, Google, well, let's do that together. So if you do GitHub, Tamayo, that's me. And you go to my GitHub page. Okay, then if you go to the top to repositories, the top one here is UArizona Workshop. Okay, so let's click on eclipses.ipynb. Were people able to navigate there? Okay, so this might be the coolest thing I tell you in the whole workshop. If you take any Jupyter notebook on a GitHub page and you go into the URL where it says github.com, if you add GitHub to Colab, so between between the GitHub and the collab, if you put GitHub and then you write TO2 collab, COLAB, it will open that notebook in Google Colab, which allows you to run that code on a Google server. So, all of these workshops typically spend the first 20 minutes trying to get everybody able to install things on their computer. And this makes it much, much easier. Okay, so this Jupyter Notebook is an introduction to how to do different things in Rebound, but centered around this battle between the Medes and Lydians. I don't even know if that's how you pronounce it. In 585 BC, like they'd been in this long-standing war, and during this battle, there was a solar eclipse that Thales predicted, and they took that as such an ominous sign that it ended the war. And well, that's a long story. But we're going to use Rebound to try to integrate the Earth, Moon, and Sun backwards to that moment, which is kind of fun to put together. Okay, so this first cell is just installing the things that we need. We want to run anyway. Right, so Rebound is not installed on Google servers by default yet. So you have to install them. But we can start looking at what some of this code is doing. So so let's see. On any one of these cells, you can, I think, click the play button. A useful shortcut is also to hold Shift and press Enter, and it'll run that cell. Is everybody able to get on here and run these cells?
So,
Yeah, it's a dark magic.
So do we have to work on a saved copy, or can we work on just?
So you can always work on your computer. Like if you open a terminal, you can just do this pip install Rebound without the exclamation point. And then when you open a notebook, you'll be able to run it. Yeah, so you're right. Like this thing, after it runs, then you'll lose it. But it's just a way to show you the code.
What is the function of the exclamation mark in this example?
So these are commands that you would usually run on the command line on your own computer. So this is like telling it to run it in the background and on the terminal. Yeah.
I noticed on the docs, there's a way to install Python version versus version, unless I misread that. Is there like a standalone Rebound versus just installing that you need to worry about?
No. Yeah, it should be completely independent of your Python installation. Yeah, as we go along and then different people try different things out, I'm also happy to help people install it if they want. It's actually super easy, but I just wanted to run it this way.
Which programming language is the source code of Rebound written?
So everything in Rebound is written in C so that it's fast. And then this is a Python wrapper that is just calling all these C functions, all the expensive functions being called from Python in C. So running it in C is really not noticeably slower than running everything in. Did I say that backwards? Running it in Python is not any slower than running it in C. And when you run it in Python, then you can use matplotlib to make plots. You can use SciPy to take Fourier transforms. It's really, I never do any signs in C anymore, which is nice. Yeah, any other sort of like big picture questions? I have no agenda for today, so we can go through as much of this or as little as this. We can take detours, whatever people are up for. Okay, so anything that you do with Rebound will start by making a simulation object. Okay, so when this is just giving us an empty simulation, now we need to add particles to our simulation. And there are many ways to do that. We'll talk later about how to like positions and velocities, use some major axes. This is a fancy way where if you just give it a name with an optional date and time, it will query JPL horizons to put in the sun and the earth at the date and time that you wanted, which is kind of cool. Okay, so one thing that is really useful is like to check that you're doing the things that you think you're doing and see what's in your simulation. Okay, so this function here, rebound.orbit plot, is just going to show us what our simulation looks like. So far, we've just added the sun and the earth. Okay. This is showing you an orbit, but we haven't done any integration yet. Okay, this is just where the earth is. And because we've put in the position and the velocity of the earth, you can calculate orbital elements. So it's just showing you what the orbit looks like, but it hasn't moved. Like nothing has happened yet. Yeah. Okay. Then the other types of querying that we might want to do is just like asking, what are the positions, velocities, orbital elements of our various particles? As we integrate, we're going to want to like check those, store those, do manipulations with them, whatever. Right? So our simulation has a particles array that is ordered in the order that you put your particles in. Okay, and it starts at 0, like everything in Python. So our first particle, particle 0 is the sun, particles 1 is the earth. So we're asking, what is particles 1? What is the Earth's eccentricity? And the Earth's eccentricity is 0.017. Yeah. We could also change this and ask, like, what is the Earth's sub-major axis? Okay, it's 1. Okay.
And one question, because if the orbital parameter change in time, that will give you the orbital parameters at what time of the simulation?
Right, so like if we want to integrate, then we call this function, which is saying like, take my simulation with the positions and velocities it has now and integrate to this time, to time 10,000.
So those are like the initial condition, the previous one, right?
That's right. So, you know, we could, right, if we integrate to 10,000, well, our semi-major axis isn't really going to change because we have a 2-body orbit. So like it doesn't change. But we're about to make it more complicated. And we haven't said yet what these units are. Yeah.
Is the semi-major axis in this case 1 because it's default using an AU as the length unit, or does that like normalize to whichever particle you put in?
No, like you need to use some set of units. And this is just using the default in Rebound. We're about to talk about units. Yeah.
I imagine there's also a way to set like individual like locations of objects. So like you know, as opposed to just querying JPL, like you could put in the REBOUNDx of something.
You can't put REBOUNDx.
Or some.
But you could put XYZ, VX, VY, VZ. There's many options for how you put in particles. So we are going to explore that as we go through this. I'm just trying to do the simplest thing. Well, this is not querying JPL horizons, not the simplest thing, I guess.
What's happening with that? I was trying to get the orbital elements for the sun.
Oh yeah.
Why can't I get?
Yeah. I guess that's sort of a planetary bias that like we have orbital elements for all the planets, but not the sun. You know, I guess in this case where we have the sun and the earth you do have a two-body orbit for the sun and the Earth, so you could get that. But that becomes more ambiguous if you have more planets in the system, right? Like which ones do you... These orbital elements are the solution to a two-body problem. And that becomes not well defined when you add more planets. So if you try to ask what are the orbital elements of the 0th particle, which is the sun, it will tell you, no, sorry, you can't do that.
Does the order matter? Like if we had put the Earth in first to make it particle 0, would it then give you like the sun's orbital elements of the Earth's frame?
So yeah, that would, I don't know, let's try that. Yeah, that would work.
So the reference point is not the solar system very center.
That's right.
Center of the sun.
So
Then you have to add a very center.
so a lot of N-body codes will sort of hard code that the center is the barycenter, the center is something. Rebound lets you make all your own choices. Okay, so I could do we just changed the syntax for all these things. Oh no, here we go. Okay, so this used to be sim.calculate orbits and now it's just orbits. If you call this, it will give you back the orbital elements for all the planets that are in your system. And by default, Rebound uses Jacobi coordinates, where each particle is referenced to the barycenter of all the interior particles. Okay, but here I can also set my primary to be whatever I want. So I could take heliocentric coordinates by saying that my primary is particle 0. Yes, no, good idea, good idea. Okay, so here I'm saying calculate the orbits, but use the sun as the primary. I could also get barycentric coordinates by saying as the primary, use sim.center of mass. This is giving me orbital elements in barycentric coordinates. So we just don't want to make that choice for you. There's different applications where you don't want to use barycentric coordinates. So it just gives you the flexibility to make whatever choice you want. Yeah.
Probably cross out the table of contents so that can be.
Perfect. Okay, so like, something that you can try out is like modify the code above to also add Jupiter, right? Like this was a two-body orbit. So when we integrated, we just got back the same eccentricity that we started with because it's a two-body problem. But if you add Jupiter into the problem, then it won't be the same. So I don't know, we could take like a couple minutes, right? Try to add in Jupiter, try to look up what the different orbital elements are. I'm sure you'll find things that, there's things here like you have the semi-major axis, the eccentricity, the inclination is ink. So there's things like that you run into. You have big omega. You have little omega for the argument of barycenter. And I'm going to point you to, there's lots and lots of example notebooks. Like there's one specifically focused on orbital elements, because you're not going to remember all of this.
So I tried to add Jupiter and somehow it's given me like, no, 4 planets.
So that's one thing that can be tricky in these Jupyter notebooks is that like if you keep running commands, they just all pile on top of each other.
So I have to like call the first cell again.
That's right. Like you want to like make a new simulation that is empty again,
Right.
then add everything in.
There was.
Yeah.
Yes, okay. So I got two friendships, so then you-
You know, so like there is some learning curve there that like the fact that you have this flexibility to add things however you want makes it possible to do unexpected things. But once you start getting used to it, it gives you so much more flexibility to do exactly what you need to do for your science and not have to dig into any source code to see what it's doing and change it and things like that.
And by default, what kind of integrator is using this function integrate?
It's using a really high order integrator called IS15, which is choosing its time step, and it's adaptively changing the time step to make the errors go down to the level of the machine precision.
Oh, okay.
So, you know, it's basically the best that you can do in terms of accuracy. And it's a really flexible integrator that doesn't make any real assumptions about what you're putting into your simulation. So it's a really good default. The downside is that it's slow. There are other integrators that are significantly faster, but are exploiting certain approximations, which if those go badly, then they will give you inaccurate answers, whereas this one will always give you the right answer. So
The most accurate.
that's right. Yeah.
And is there a way, for example, with some parameter of the function or something to put a threshold, like to tell it do not go to the precision of the machine, but like less precise?
Yeah, so the funny thing is that because it's a 15th order integrator, then if you make your time step twice as small so that it runs twice as fast, you change the error by 2 to the 15th power. So you change it by 32,000. So there's actually not much dynamic range in choosing your time step. So it doesn't let you do that. Like it doesn't make sense for such a high order integrator to make that choice. But for other integrators that like some of them use fixed time steps to get nice numerical properties, there you do choose your own time step. And I'm happy to talk as much or as little about things like that as people want.
So the orbit plot, that's like the most recent time step that you have integrated or initiated.
That's right. Like here we call sim.integrate to 10,000. Let's do that. So
It's like if you did sim.orbit plot, like then that's showing you what it's looking like, the particle locations at time step 10,000.
that's right. So like the most useful types of things to learn how to do is just learning how to query the current state of the simulation. So one thing that you can do is you can say, what is sim.t? What is the time? Well, right now it's 10,000 because we ran it to 10,000. So when we do rebound.orbit plot, even if we do these out of order, this is what the simulation looks like at t of 10,000. Yeah. Also, like this does not mean integrate for 10,000 time units. It means integrate to 10,000. If I run this again, it's doing nothing because we're already at 10,000. Okay, so if I wanted to integrate another 10,000, I would have to make this 20,000. And now we're at 20,000.
So it always starts from 0, let's say.
That's right. Well, let's try it. So if we take a new simulation and we check what is the time, it's 0. But you know, that time is arbitrary, right? So like, if it helps you to like reference that to some physical time, you could like set this to be 187 And now the time is 187, and if now we integrate to 10,000. Oh, I haven't added particles yet. But if we integrate to 10,000, we'll still be at 10,000, but we'll have integrated less because we've started at 187.
Is there a parameter in the integrate that tells you like where to start, or do you just have to do that method?
What do you mean by where to start?
Like, is there, like, does integrate have a, like, T initial, T final? Like,
No.
parameters, so it's
T
just,
initial is always the current state. It's wherever you are.
So IS15 is, as you said, the time step is adaptive. Is there a way to know the actual time step or the minimum time step during the integration?
So this is the time step being used. You know, we're going to talk about units, but like, you know, what is, we could check. What is the Earth's orbital period? Okay, so apparently in these default units, for reasons we'll talk about, the orbital period of the Earth is 6.28, which is suspiciously close to 2 pi. Yeah. So, you know, this is something like 3% of an orbital period.
Is that the current or the last time step or?
I think for most applications, you don't have to worry about that. It's like basically the last one. There's also a sim.dt last done. Which IS15 is not using. So for some integrators, there is different integrators are doing more and less complicated things, and there it can matter. There's like different types of time steps because you're going back and forth and you're doing partial time steps. But the one to check is just sim.dt. Okay. So like the sort of thing that comes up all the time is you're trying to make a simulation and you're just trying to store outputs. So like say the X, Y positions of the Earth and the eccentricity of the Earth, like as a function of time, right? So one way to do that, and it gives you flexibility to do however you want, but one way to do that is to make an array of times. Like we're using NumPy linspace to make an array of times between 0 and 10,000, and we're asking it for 5,000 of them, right? So this cell is making a simulation, it's making our array of times, so we can check the times, okay? So there's times going from 0 to 10,000. And one thing that you'll see in a lot of the examples is a loop like this that says like for I time and enumerate times. So it's saying, go through this array of times, and for each one of them, whoops, give me a time. So the time will be populated with 0, then 2, then 4, etc. And then enumerate is giving you both the individual entries in the array, and it's giving you the index. Okay, so the first time it goes through, I will be 0, and time will be 0. The next time I will be 1, and time will be 2, etc. Okay, so you can use this index to index your arrays, and you can use this time to tell Rebound to integrate to that time. And then you can store what is the X, Y positions, what's the eccentricity by calling sim.particles.x.y.
I mean, for doing something short term, I can see how this would work. It seems like it would be an incredibly computationally inefficient way to save data.
So that's the thing that like, when we say integrate to time, we don't like, so the first time that this runs, this will say sim.integrate to 0. So it won't do anything and we'll store the initial condition.
I mean, no, I understand it's only doing one time step at a time.
Mhm.
But I guess I'm just saying the process of calling the integrator storing the output, calling the iterator, storing the output, I would expect that loop to take longer than something where
Oh.
within, like, if I was running this in C.
Yeah.
Right, I would just having the IO spit out
Mhm.
data at some cadence.
Uh-huh.
So if I wanted to integrate if I was trying to do a long-term integration, would this be a terribly inefficient way to do it?
No, it would be totally fine, right? So I guess the question is, how long does this type take to do each time compared to the overhead of doing this loop in Python?
Exactly.
So if you're doing a long-term integration, like if you're integrating the solar system and you're taking like 5,000 outputs over 5 billion years, then, each of your integrations is 5 million years. So that takes much longer for Rebound to do in C than it takes Python to do these loops. So it's actually,
Okay, so yeah, the overhead is high for a short-term integration.
That's right.
Then you don't care.
that's right.
Okay,
So yeah, I think it's true that this will be slow, like comparatively slow, if we just integrate to a short time, like 10,000, and then we're taking lots and lots of outputs. But that doesn't take too long to run anyway. But it becomes less and less of a worry the longer we integrate.
So in this loop, when we call sim.integrate time again and again, each time does it integrate from t equals 0 or does it
No.
integrate from the previous time it was called?
That's right. So that's the key, that this sim.integrate function is always taking the current state and is integrating up to time.
Okay,
So when we're like here in the array at 4, the next time it's already at 4, so it integrates to 6.
got
So
it.
yeah, otherwise it would be horrible. Yes, yes.
So we've done that example earlier, the T equals 10,000,
Uh-huh.
and then we said if you do 20,000 now, it was automatically integrating from 10,000 to 20,000.
That's right. If we integrated to 10,000 and then we told it to integrate to 2, then it would integrate backwards in time back to 2.
so I remember Hondo had a big thing about the time reversibility of the integrator. Is that,
Uh-huh.
will that hold with IAS 15 in this?
Yeah, so like the interesting thing. So all the schemes in Rebound, well, most of the simple schemes in Rebound are time reversible, but the machine precision and floating point precision makes things irreversible. In the sense that like you're always making errors at the level of 10 to the minus 16. So if you integrate forwards, you're making errors. And then when you integrate backwards, it's not like you can undo those integration errors. You make more small errors and it like keeps climbing up. Hanno and I worked on a different integrator called Janus that like discretizes like the grid of positions and velocities where things can be on, and you can make it perfectly time reversible, which is super cool. Like you can run, like that one is perfectly time reversible. But I wouldn't say that we found the killer application for it yet.
So the forces between the accelerations of the particles, they are computed using the Newton's gravitational formula.
That's right. Yeah, this is just treating all the bodies in the simulation as point particles and taking GMM over R squared between them. Okay. So, the nice thing about Python is that now we can use matplotlib to, for example, very quickly plot how is the eccentricity changing with time. And I guess because we've just added the sun and earth, then our eccentricity is changing over our integration at the level of, it's starting at 0.17. And these are the changes at the level of 10 to the minus 14. So these are round off errors during the integration. If you add Jupiter, let's add Jupiter.
Eccentricity, it seems to decrease with time.
Ah. Yeah. So we're catching the Earth at a point where the eccentricity is going down. Right? I mean, you'd have to add the whole solar system, but the Earth's eccentricity does these oscillations. And, you know, we're just catching a very tiny segment of that over 10,000 years. Speaking of other things that rebound leaves flexible and can mess you up, if you go, well, let's just do, it'll be clear if we just do the sun and Earth. If we plot the X and Y positions of the Earth over those 10,000 years, we see that they're making this like very funny spiral pattern. Right? And they're so the Earth's like, we started over here, and you know, there's some aliasing from the output cadence, but the Earth is doing this. Okay, and the reason is because what's happening is the sun's like the sun-Earth center of mass is drifting this way, and the Earth is just going around the sun. So like we're seeing the full motion of those two things together.
Is the drift because the initial conditions are like not perfectly in the center of mass frame, or is it
That's right.
numerical effect?
No, it's just because we're not in the center of mass frame. So we can go to the center of mass frame at the beginning by saying sim dot move to center of mass. So let's try that. So if here, after making our initial conditions, we do sim dot move to center of mass. Now the Earth's orbit looks like, as far as we can tell, a circle. Okay, because depending on your application, you might want to model what the center of mass of the solar system is doing is, you know, it's moving through the galaxy or whatever.
So I have a general question about numerical integrators.
Mhm.
And so I've heard these different types of integrators, symplectic integrators, or integrators which conserve energy, integrators which conserve angular momentum,
Mhm.
and things like that. So if an integrator is symplectic, does it by default conserve all the integrals of motion, or does it only conserve the phase space volume?
So the way that I like to think about it is like, you know, numerical integrators typically rely on like some expansion that you have to truncate at some point. So the fact that you're truncating that expansion means that the terms that you're ignoring give you errors in your scheme that build up over time. The amazing thing about symplectic integrators is that the errors in the scheme are themselves Hamiltonian. So you're trying to model a Hamiltonian system, and your errors also have Hamiltonian properties, so they conserve error, okay, or energy, and like all these other integrals. But a more accurate statement is that when you use a symplectic integrator, and I can show you how to use the one in here. When you use a symplectic integrator, you are actually simulating a Hamiltonian system perfectly. It is just not the Hamiltonian that you're trying to solve. That is actually a really good way to think about it. So what you do by decreasing the time step in a symplectic integrator is you are bringing the Hamiltonian that you are solving closer to the Hamiltonian you are trying to solve. Okay, but the fact that you are solving a Hamiltonian perfectly means that you are conserving the energy of that Hamiltonian perfectly. It is just not your energy.
I see.
Okay, so when you take a symplectic integrator, and we'll try it, and you integrate it, you will not conserve energy perfectly. Like it'll be at like 10 to the minus 8 or something. And that's because the energy that you are trying to conserve is not the energy that the symplectic integrator is conserving.
And would that apply also to other integrals? Integrals of the.
It depends. So for example, this symplectic integrator will conserve angular momentum exactly at machine precision, but the energy has this property that you're conserving the wrong one. So I don't know, let's try it.
Yeah. Well, if you're using this key and the Hamiltonian that you're actually solving as an integral, it will conserve that. So it may be another integral than the one we're interested in, but it will conserve.
Yes, that's right.
So that statement about energy applies to other integrals. If there's something in the model Hamiltonian
Yes.
approximating the angular momentum, will also approximately conserving.
Yes. Yeah. I mean, like in the case of angular momentum, the angular momentum is still like R cross P. So that is conserved. It's just that because the Hamiltonian that the symplectic integrator is solving is a different Hamiltonian, it's like that combination of R and P's that is being conserved, which is not the one that you're trying to do. Yeah. Which is actually a really beautiful way of thinking about symplectic integrators. Okay, so let's try to do that. Right, so I'm adding the Sun, Earth, and Jupiter so that it's not just a two-body problem. And let's take, what is the initial energy? So we can get that by saying sim dot energy. Okay, so we're solving for what the initial one is. And let's make another array here for energies. Okay, so we're going to solve, well, let's call this the energy error. Okay, so now each time that we run, we're going to integrate to that time. We are going to ask, what is the energy now after we've integrated to that time? And we're going to populate the energy error with, let's take E minus E naught divided by E naught. This is the fractional energy error. So what is my energy now minus what we started with as a fraction of what we started with? Okay. Okay, so by default, we're using IS15. So our fractional error in the energy is at the level of the machine precision, about 10 to the minus 15, right? Like this is discrete because of like floating point errors. Now let's make this run with a symplectic integrator. So we can choose the integrator by saying sin.integrator. And let's use WH fast. This is a Wisdom-Holman integrator that we did some optimizations on it to make it run a bit faster and much more accurately. We were able to make the round-off errors unbiased in this integrator. So if we want to use this integrator, we need to both set the integrator and we need to choose a time step because so like in Hamiltonian dynamics, you have like positions and momenta as canonically conjugate pairs. You can think of energy as being conjugate to time. So it turns out that an important requirement for symplectic integrators that want to conserve energy is that you need to be sampling time at regular intervals. So you need to have a fixed time step because of that relationship between time and energy. Okay, so we need to say what we want that time step to be. And a useful rule of thumb is that you want this to be shorter than about 5% of the fastest time scale in your problem. Okay, so here we have the Sun, Earth, and Jupiter. So the fastest time scale is the Earth going around. So I'm going to choose 5% of the Earth's orbital period. Okay, I'm taking sim.particles1, that's the Earth. Capital P is the orbital period. And I'm taking 5% of that. Right, because I don't know what number to choose, but I know to choose 5% of the innermost period. Okay, so now when we run that, we see that our errors are at the level of 6. They go up to 6 times 10 to the minus 9, but they're flat, right? Like we could integrate for longer and it would stay flat. It's not growing with time. Yeah. If I make the time step shorter, if I make this 0.05, then my errors will go down. So here we're at 6 times 10 to the minus 9. And if I run it again, now I'm at 10 to the minus 11. Right? Because now with a shorter time step, the Hamiltonian that I'm integrating is closer to the Hamiltonian that I'm trying to solve.
I understand that now there is a new integrator, WH-fast 512.
Oh,
What's the difference between those two?
So people do all sorts of work to parallelize N-body codes. But that's typically in the case where you have like huge N, you have millions or billions of particles, and you're trying to find ways to parallelize it. It's with a solar system or planetary systems, you're kind of stuck because you don't have enough particles. So it's sort of like Caitlin's question, right? Like we could parallelize things, but that adds an overhead always. So if you only have 8 planets, then trying to like spread out the calculations you're doing at each time step, which are really very little, right? It's GMM over R squared for all the pairs. You actually pay way more in overhead in parallelizing it than you gain in speed. Okay, so parallelizing across different processors is not helpful. In WH-fast 512, we're trying to use instructions that allow the operations to happen just on one core, but like optimizing how the cache on that core is being used to parallelize things, right? Like this Wisdom-Holman scheme, the way it works is all the planets are taking a Kepler step, which is assuming that the planets are following unperturbed 2-body orbits. So you take a Kepler step, imagining that all the other planets are not there. And then you do an interaction step where all the planets kick each other. And then you do like a Kepler step and a kick step and a Kepler step and kick step. That's how it works. So by far the most expensive thing in that step is doing the Kepler problem, right? Because you have to like solve Kepler's equation and you have to do some iteration there to do that. So you can squeeze out some performance if you can parallelize those 8 Kepler problems for the 8 solar system planets can be done side by side and they're independent from each other. So you could do that. So in that, for WH-fast 512, we are trying to do those 8 Kepler problems side by side, but only using the memory that we have available in the cache on a single processor. And that makes it something like 5 or 6 times faster. And it means that we can do the solar system instead of taking about a week with like the fastest N-body integrators with WH-512, you can do it in about a day, which is pretty cool.
But in many cases, one wants to run, say, 1,000 or several thousand integrations
Yeah.
to explore parameter space.
Then no problem.
Then you parallelize.
Yeah, then you can do that across separate cores and it doesn't matter. Yeah.
So is there any situation where WH-fast is preferred over WH-fast 512, or is it 512 just an improved overall version of the old one?
So I guess 2 things. It's wonderful that the solar system has 8 planets because that's a power of 2. So that makes it easy to split up. So WH-fast 512 actually runs nicely for 8 planet systems. It runs great for 4 planet systems because you can run 2 4 planets side by side, and it works well for 2 planet systems. For other numbers of planets in your system, you're not going to get the same gains. So that's it's silly, but if you're interested in understanding chaos in the solar system, it is kind of a game changer to be able to run like an order of magnitude more simulations. The second thing is that because you're limited by the memory on this cache, like we're really trying to squeeze as much into that as possible. And it means that it's restrictive in terms of what you can add to your simulations. So the other thing that I'm going to show you is like, how do you add extra effects into these N-body simulations like ties or GR and things like that? You can add GR to WH-Fast 512 because that's an important effect for the solar system. So we wanted to be able to do that. But you can't do a lot of the other things that I'm going to show you. So if you just care about point gravity, like in 8-planet systems like the solar system and maybe GR, then it's great and you should use it all the time. But it is more restrictive than WH-Fast, which can do all sorts of other things too. Yeah, so it's a specialized use case for sure. Okay. So this is showing you, we've already talked about some of this, that you can check the sun major axis, you can check the orbital period, that's capital P. And this is getting at units, right? So it kind of makes sense that A would be close to 1, right? We know that the Earth's orbit is 1 AU. It's weird that P is 2 pi. And we can check, like, what is the mass of the Earth? It seems like it's 10 to the minus 6. And we can check that the gravitational constant is apparently be set by default to 1. Okay, so what's going on is that like you could use whatever units you want. But for example, if you think about the solar system, if you set G to 1 and the sun's mass to 1, then if you use Kepler's third law for the Earth, you know that the period is 1 year and you know that the sun major axis is 1 AU. So, well, I guess you can only do that for 2 things, right? So the reason why the period is 2 pi is because we've set G to 1, we set the solar mass to 1, and the sun major axis is 1. So when you solve for the period, you get the square root of 4 pi squared and you get 2 pi. Okay, but you could use whatever you want. Okay, so after you add the particles to your simulation, you can put in here, you need to make 3 choices. You need to choose a unit for distances, a unit for time, and a unit for masses. And you could make this days. There's a few different options in here. But those are up to you, but it's important to know what you're putting in so that you know what to use for initial conditions.
Can you, by any chance, put like astropy units, like an object of astropy units? Or...
No, that would be really nice. Yeah, it would be nice to add something like that. Yeah, we should actually think about that. Because on the one hand, this is not a big deal for this, where you just have to choose 3 units. But when you start to add in other effects like tides or radiation pressure or things like that, you start having to put in many, many more parameters where it does become a nightmare trying to keep track of the units. So that would actually be really nice.
So from the perspective of galaxies, quite often what we need to do is simulate a bunch of particles in some underlying potential, which may be time dependent.
Mm-hmm.
And can rebound take care of that? Like if you have an underlying potential that you specify, and you want to compute exact forces between some tracer particles that follow that underlying potential.
Rebound can't do that. What I'm going to show you next gives you the flexibility to add in things like that. But my guess is that there would be more specialized codes that have done that for you rather than like trying to build it from the ground up. But I'm not really sure. No.
So I know quite a few codes can simulate tracer particles on underlying potentials, but they don't necessarily include the interactions between the particles themselves.
I see.
So,
The particles interact, but not tracer particles.
right, that's true. I guess I'm trying to get somewhere in between, like a pure N-body simulation and a pure tracer particle simulation, where you can also include interactions between the tracer particles.
So you mean like an N-body system with an underlying potential?
Yes, something like that. Right.
Gala can do that.
Sorry, that's still just an N-body simulation where you're specifying an.
Yes.
It's not a tracer particle.
Yes, it's not a tracer particle simulation at all.
We have something like that. In the, like, we call them active particles, where if you add active particles to the simulation, that's the default. Then all the particles interact with each other through gravity, and you have n² interactions. There's also cases where like you have planets and a bunch of planetesimals, and you are interested in like, what is the back reaction of all these planetesimals on your planets? But you also don't want to like have n² interaction between all your planetesimals. So there's this option of adding semi-active particles. And if you're a semi-active particle, you will act back on all the active particles, like the few planets that are in your simulation, but the semi-active particles won't interact with each other so that you don't have the n² scaling. And then you have test particles that don't interact with anything. Well, they get acted on by the other ones, but they don't do anything to the other. So yeah, I think that's an interesting problem also in planetary dynamics. Okay, I think that's probably a good place to stop with this, and maybe I can show you a couple other things. First, Rebound has this documentation page that has tons and tons of information. Here you can go to like the API documentation. You can find things about simulations, particles, visualization, all sorts of stuff. Okay. Another, like, what I find the most useful documentation entry point is if you go to the Rebound repository, so GitHub Rebound, and you go into IPython examples from before they were Jupyter notebooks, you have a ton of Jupyter notebook examples with working code that shows you how to do different things. Okay, so it is kind of tricky in that you need to sort of guess from the titles what it's trying to do. But if you can do that, it can be really useful. Or you can just like ask me or Hano, and it's easy for us to point you to the right notebook here, right? So for example, there's a whole notebook here on orbit plot for like visualizing what is going on. There's a whole notebook on orbital elements and like all the different things that you can try to access. Like this Megno, for example, is a chaos indicator. These are a lot of the plots that I was showing you in the talk that differentiate the chaotic regions from the non-chaotic regions. And this is also a nice notebook, which you would not know, for like how to parallelize a bunch of rebound simulations, right? Like if you're trying to populate this grid, you want to run all of these with as many cores as you have available. And this shows you like a simple example of how to do that. So this, I think, is actually the most useful place. So if you go to the Rebound GitHub repository, so if you Google GitHub Rebound, you'll get a page like this, where the first hit on Google says Hanorein Rebound. And if you click on that, it's this folder that says IPython examples.
It's also on the top of the notebook, right?
On where?
Like in the first text at the beginning of the notebook that you shared us, the Eclipse notebook.
Oh, yeah. Yeah, no, like this is just by far the most useful set of documentation. I wanted to say a couple words about this simulation archive. I've showed you the most common way of storing your output, which is just to make a bunch of arrays and then run to different times and store things. I think what everybody finds is like when you're running your science, you can guess at what you want to store, and then you can find interesting things and you can say, oh, well, I wish I'd stored this other thing, or I wish I had outputs in between these two. So this simulation archive fixes all those problems, and I think is a really useful tool to learn how to use if you're using Rebound. So the idea of a simulation archive is that it is a binary file that is storing snapshots of your simulation. Okay, so here we're setting up our simulation just like we did before, but the important call here is sim.save to file, where we're choosing a file name. And we're saying how often in the time units that we've chosen to use, right? By default, we're using these like funny time units, but we could set time to use AUs, years, and percent. So if we did that, this would be like save a snapshot every 1,000 years, say. Okay, so, well, let's just show what that looks like. Where's my, oh.
Is the delete file? Oh, wait,
Sorry?
never mind, it says the word.
Okay, so if you're using a simulation archive and you're telling it to save every 1,000 years, now you don't have to make an array of times. You just tell it to integrate for as long as you want. So here it's integrating for 1,000,000 time units. Okay, and it's just saving a snapshot every 1,000. Okay, so this is showing you that like after you have your binary file, you could just delete the simulation from this Jupyter notebook. You don't need it anymore. Okay, and now it's going to show us like we're going to go through the process of like how would you analyze stuff using the simulation archive. So you would start by loading your simulation archive. Right, so instead of doing rebound.simulation, we're now making a simulation archive object using our file name that we've used. And we can get information of it by asking like, how long is our simulation archive? There's 1,001 snapshots. There's the initial condition and then 1 every 1,000. And we can check like, what is the minimum time? What's the maximum time? Okay. Now, you can think of this simulation archive as an array. If we take the 500th index, that is giving us back a simulation object as it was at that snapshot, right? So after we get that simulation from our archive, we can check anything. We can check what is the time? What does the particles one look like? We could take like, we could ask, what does our system look like at that time? Right, and it looks like this. Okay, so now what we would do is we would run something similar to before, but let's think about how it's different, right? So here we're making an eccentricity array, and now we're going through our array of snapshots, and we're storing what the eccentricities are. Okay, and then we could plot it. I guess we'd also need, we would need to get the times. And now we have the eccentricities all through time. Okay, so if that's all that you could do, then like, why would you do that? What's useful about these simulation archives is that we can get our simulation at any time that we want. Okay, so if we say sa.get simulation at this time, then if there's a snapshot at that time, great, it will just give you back the simulation. But if you give it a time in between, it will just find the closest snapshot and it will integrate in between to that time that you want. Okay, so that really is a game changer. Like if you think about, people run integrations of the solar system that maybe take a week. And in 1% of those cases, like Mercury crashes into the sun or into Venus, and it does it on a really short time scale. So like you couldn't store enough outputs to catch that happening. You would run like, 1,000 of them, and then 10 of them would have Mercury doing this, and it's happening between your time snapshots. What's worse is like, you couldn't then take those 10 simulations and run them again with finer time resolution because the system is chaotic. So that like by stopping at different times that are close together, you're creating like differences at 10 to the minus 16. And because the chaos, those little 10 to the minus 16 changes are growing exponentially and they give you a different evolution. So the 10 that you wanted to run that have Mercury colliding with Venus don't collide with Venus anymore. So what these simulation archives give you a way to do is they give you a way to take those 10 runs where Mercury collides with Venus and just pick those out and then start from any one of the snapshots. And we've been super careful to make sure that everything runs exactly the same way, even if you decide to change where you get your outputs. If you start from a binary file and then you change where you want to get the outputs, you will get the same chaotic evolution so that you can actually study the thing that you're trying to study, right? Because before, like, if Everett finds that Mercury goes unstable in this simulation and he sends me his initial conditions to me and I run it, I will not see the same thing. But with this, you can actually get the two to match up.
Well, then, what about the question about time steps? You have to please redefine your time step.
That's right.
So what happens if there's a close encounter? It should in principle then either change something, make my time steps much smaller or size.
Yeah, that is a little bit tricky because the algorithms that we need to use for these really long integrations are symplectic and use a fixed time step. So like it would take many months to run the solar system with IS-15 with this adaptive time step, and it would just not be efficient. So it is a problem that if we use WH-fast, the symplectic method with a fixed time step, then when the eccentricity of Mercury gets really high and it starts having close encounters, you're getting big numerical errors. So sort of the implicit assumption there is that like, you know, what we're interested in is what is the chaotic evolution up until the point where Mercury's eccentricity reaches like 0.8 or something. And then we say like, well, even if we can't trust the details of what happens after that, once Mercury reaches that point, everything is going to go badly. But the other thing that you could do is you could use WH-fast to integrate to the point where you are close, but not like actually having the close encounters. And then you could store that as a binary snapshot. And you could use that as an initial condition and run IS-15 or something starting from there.
But also yesterday you explained many things by just making approximations. You said all the action happens at conjunction. So that would suggest that you could integrate most of the orbit with larger time steps and reduce the time steps close to conjunction, but still capture long-term evolution of it.
That's an interesting idea. The solar system, oh, I mean, it's a separate question for the other ones, but the solar system is a little bit different than everything that I was talking about yesterday.
Yeah.
Because the chaos in the solar system comes from the overlap of secular resonances rather than the mean motion resonance that I was talking about. So for secular resonances, which happen at wider separations, it is not true that you can just look at what's happening near conjunction. Like what's happening everywhere on the orbit contributes comparably. But it would be interesting to think about something like that for these compact systems. I haven't thought very much about that.
So another question about numerical integration. In a given time step, what has a greater computational cost? Is it the force computation or is it updating the positions and velocities particles?
In general, that's a complicated question, right? Like it depends on what the scheme is doing. So like in WH-fast, you're taking this Kepler step and then you're doing this interaction. So the Kepler step is expensive because you're solving Kepler's equation, but it's of order n. Like it scales as order n. If I have 8 planets, I have to do 8 Kepler problems. I have 16 planets, I have to do 16 Kepler problems. Then between Kepler steps, you're doing this interaction, which is gravity between all pairs. That scales as n squared. Okay, so at small n, you are dominated by the Kepler steps because you don't have many pairs of planets and GMM over R squared is trivial to calculate. But for large n, you become dominated by n squared and the Kepler step doesn't matter. But as for WH-fast, and every different scheme is going to have different scalings, and yeah, it's a tricky question.
One question about the simulation archive. So can you use it for if you're using IS-15 instead?
Yep.
And you can still go back to a previous snapshot and integrate with a different, well, I guess the time step is selected by the integrator. So I can still go back to a previous snapshot and look for and ask it to integrate to an intermediate time. Okay.
And if you do that, like, say you have 2 snapshots here. So if you start from here and you integrate to here, you will get the same output as the integrator originally followed going from here to here. But when you take this snapshot, you get back a simulation and you can do whatever you want. You could change the integrator. Now you're going to get a slightly different trajectory than you got in your original one. But sometimes that's useful, right? Like if Mercury is having a close encounter and you want to do something different, the world is your oyster in Rebound. You can do whatever you want at your own risk. All right, so I wanted to show you big picture REBOUNDx, which is a library that I wrote with Hanno for Rebound, where the idea is to have Rebound be a package that has all the different integrators. It has all the API for querying it, do all that stuff, but to decouple that from a library that implements different types of effects that you would want to add to your Rebound simulations. So here, I'm going to show you a bunch of example notebooks just like before, but the other really, really useful piece of documentation is, I don't know, what's the easiest way? So if you can't remember that, that URL, if you do GitHub REBOUNDx to find the REBOUNDx GitHub repository, so it's, I don't know, it's X for extra forces. Okay. Here on the README on the GitHub page, you can find the docs here. So this should be a working link, I hope. Yeah. Okay, so that's pointing you to the documentation page. And this is the most useful place in the documentation. Number one here shows you the implemented effects. So if you click here, this is a list of all the different effects that people have added to REBOUNDx. Okay, and you can sort of, they're grouped into the types of things that you might care about. So there's like orbit modifications, like you can do type 1 migration, you can just add parameterized forces that cause migration or eccentricity damping. There's effects for adding general relativity and different approximations. There's radiation forces. There's tides. There's like gravitational harmonics like J2 and J4. And different things. Okay, so if we take any one of these, I don't know, let's take sort of simple one. So let's do modify orbits forces. Okay, so it tells you what this implementation is based on. So this, like the parameterization comes from this paper by Papaloizou and Larwood in 2000. And then it has a link to both an example in C and an example in Python. Okay, so we're going to look at this in a second together. But I wanted to show you that still on this documentation page, there are these useful tables that tell you what kind of parameters would you have to or want to set for your particles to make this effect work. Okay, so, well, let's look at the example first, and then we'll go back to the table so that you will sort of see what it means. Right, so just like with Rebound, this is now on GitHub. Like this has linked us back to the GitHub page. And REBOUNDx has also a folder that is IPython examples that has lots of examples for how to do these different things. Okay, so we were on this migration notebook. Okay, so the idea is that we're going to import Rebound and make our simulation like we did before. The difference here is that we're also importing REBOUNDx, this library. Let's open this in Colab. And now we're going to have to pip install Rebound and pip install REBOUNDx. Okay, and everything always starts by making a REBOUNDx object, which we do by calling REBOUNDx extras. And we always have to attach this extras objects to the simulation that we're talking about. So it's like we're attaching REBOUNDx to the simulation that we've created up here. Okay. Now we want to tell REBOUNDx to load one of the forces that it already has implemented. Okay, so we just came from the documentation page for modify orbits forces. So that's the name of the force that we want to put in. Okay. And then we tell REBOUNDx, like this is just loading it, and this is telling it to add it to our simulation, rebx.add force. Okay, so now we've added this force to our simulation. Now we need to set parameters. So this implementation is saying that we want our semi-major axis to grow or shrink exponentially according to this tau A timescale. Okay, so if we have, we've added a sun and we've added 2 small planets at a semi-major axis of 1 AU and 10 AU, A inner and A outer. Yeah. So for either of those planets, we can add a tau A that will make that semi-major axis either grow exponentially or decay exponentially if tau A is less than 0. Okay, so here what we're doing is we're setting a maximum time for our integration, and then we are setting tau A for particles 1. So the new thing in REBOUNDx is that all the particles, so this is a shortcut that's actually quite useful and I use all the time, is you can name anything in Python. right? So we kept typing like sim.particles1, sim.particles2. So I'm just calling PS sim.particles, so I don't have to type it every time. And then I'm saying PS1 dot params tau A. Okay, so each of our particles in our simulation now has this parameters, which is a dictionary where you can tell it, take your parameters dictionary and set tau A equal to whatever you want. I could make this like -3, or I could make it 5 or whatever. And I'm saying, I want this exponential timescale to be negative so that my particles will decay, they will move inwards. And I want it to be like the maximum time of integration divided by 2, so that I see something interesting. And this one is going to be minus Tmax. I'm just setting them to different numbers. And now when I integrate and I store the semi-major axes of my particles, I can check whether my particles do what I expect, right? So this is calculating arrays for what we expect. We expect our inner semi-major axis to decay exponentially at a rate like T over tau A. And if we plot those things, like the actual n-body points in red are matching the theoretical dashed lines there.
So with this function, the load force, is it possible to, because there, from what I understand, it's basically loading a pre-written
That's right.
thing, right? So is it possible to put something arbitrary that is not already inside of REBOUNDx?
Yeah. So there's a quick answer to that, which is to try something quickly. And then there's one that's like adding it to REBOUNDx so that other people can use it. And it is useful to just try something quickly. So where's the custom effects? Okay, so if I want to add a custom force, I could write an arbitrary function here where the rule is that any function that I want to add needs to have this prototype. You're going to get the simulation. You're going to get this REBOUNDx force, which, might have parameters on it. So like, maybe it carries the speed of light or something, and you need the speed of light to calculate the things that you need to calculate. You're going to get the particles array so that you can access individual particles, and you're going to know how many total particles are in the simulation. Okay, and then you write your force. This is like the C-type stuff for how you turn the thing that's being passed to you into a simulation like we've been using. Like once you do this line, now you can use simulation.particle everything, okay? And the goal of your simulation is that you need to update the accelerations for all your particles. So you need to change what is A in the X direction, what is A in the Y direction, what is A in the Z direction. Okay, so this is just a really simple example where we're only changing the X acceleration for only particle 1, and we are changing it by this much. Okay, and the way that you would do that is that then instead of loading force, you would create a force and you would give it a new name. And you have to do a couple things that are explained here, but then you can add your force to your integration and you can run things and things will happen.
So this could be used to put an underlying potential.
That's right. Yeah, yeah. So you can absolutely do exactly what Himansh was asking.
Right.
I would just always advise to check if somebody has gone through the pain of that before you, to save you many hours of trying to implement it yourself.
To not have to write it.
That's a related question for what Himansh is asking. So I found that the parallelization of the inactive particles in.
Yeah,
I emailed Hano about it a couple years ago.
yeah.
So I don't know if you guys you're aware of it or Hano is aware of it. We made some changes. I think this team actually sent him some of the changes. I don't know if they were ever inked.
I'm not sure. I mean, I think the short answer is that, well, I have never done any science problems with lots of particles, so I've never
Never tried.
done it. Yeah, I've never tried.
Just come talk to me because I know that the parallelization doesn't work.
Mhm.
Because basically there's an MPI communication problem where it doesn't properly send the particles from one processor to the next. So depending.
Is it
on-
MPI or OpenMP? I think it's OpenMP. Like MPI is a whole other can of worms.
So there's no open, so,
I think there are still problems with OpenMP.
okay.
And some of those problems are with OpenMP.
I thought, yeah, the
yeah.
problem was basically the particle arrays, the active particles weren't properly sent to all of the processes.
Uh-huh.
So I think it was an MPI problem. It was, they didn't all have access to the same particles, so.
Okay.
You put, depending on the number of processors that you divided up on, or the number of domains you use,
Yeah.
you can get the correct answer or the incorrect answer.
That's exciting.
Yeah, so it's super fun.
Okay. I'm not sure.
Okay, it is, but if you want to do it, make sure you find me first, because I can try to recall what the issue is.
Okay, I wanted to show you, the longer answer is that on this documentation page, if you try that out and it's working how you want, what we did is we added a function in Python. That is gonna be slow. You know, I was just saying that like Rebound runs just as fast in Python as in C, but if you write your own Python function, that is being called every single time step, and that is gonna be a factor of 3-ish slower than if you write it in C. So this page here, adding a new effect, gives you a tutorial of how to add things in C. Okay, and it's actually really easy to do. Even if you've never used C before, if you've written a function in Python, translating into C is now super easy. Okay. Rosie asked me for everybody to please quickly fill out this survey that has like 3 questions on it. So if people wouldn't mind doing that, you can either like scan this QR code, or this is bit.ly/Tamayo workshop.
I have a question related to the last thing you said about how writing around functions on Python make it slower. Is it also the case for collision functions? Because you can also make your own collision resolution functions. It's also slower if you write it in Python rather than in C?
That'll depend, right? So the problem with this is that when you have an extra force, you know, you're integrating, say, out to 1,000, but every little time step is calling Python. So in the case of collisions,
Yes.
if you're integrating for long times and then there's a collision after a long time, then even if you're running things a bit slower over here, and then you run a long time, it's not a big deal.
Okay.
But if you're having lots and lots of collisions, then it will slow. And I think the answer for that is always that it's better to check empirically. So run your code, writing your Python function for collisions, and then write a version where your Python function for resolving collisions does nothing, right? So that should be free. And then run both and see how long they both take.
Mhm.
And then you can decide, is it worth it for me to write this in C to speed it up, or do I not care? Yeah. So I didn't talk at all about celmech, which is this code that Sam Haddon and I wrote, which was for doing some of the more technical Hamiltonian perturbation theory type calculations that I was talking about behind the scenes yesterday. Because I think people are probably gonna find this more useful, but I'm also happy to talk about that offline. People are. So if you ever find yourself having to do like some planetary dynamics and having to like look into the appendices of solar system dynamics, remember that I told you that you should look at celmech instead of trying to go through those appendices.
No, I have another question regarding the newest integrators that have included. I think now there is another one called Trace. Could you explain a little on the differences between Trace and IS-15 in terms of for which kind of applications it is preferred to use one or the other?
I think the big picture is that the Wisdom-Holman integrator, WH-Fast and WH-512, is like an order of magnitude faster than IS-15 because it's exploiting the fact that the orbits are nearly Keplerian. Okay, so like that is the fundamental thing, that you have this fast integrator and then everything else is slow compared to this Wisdom-Holman. The problem with Wisdom-Holman is that the fact that it assumes that the orbits are nearly Keplerian by moving on Kepler orbits means that if your particles are having a close encounter, during a close encounter, things don't look Keplerian. So it gives you big numerical errors. Yeah. So people developed these hybrid integrators that said, well, let's just do the fast thing as long as we can. And then if we have a close encounter, then we'll switch to the slow thing. And then we'll go back. Okay. So it's similar to the discussions we were having before. Doing this more complicated hybrid scheme has an overhead cost because you always have to be asking, like, am I having a close encounter? Am I having a close encounter? So if it's the case that most of your time is nothing is happening, do the fast thing, and then there's a few close encounters, and then nothing is happening, and then there's a few close encounters, then that's going to be way faster. Okay, but you know, so Trace and Mercury and like these other integrators, those are the hybrid types of integrators. But if you're in a situation like after the disk goes away and you have a giant impact phase where all the planets are having close encounters and scattering, if you use a hybrid integrator, it's like, I'm having close encounter, close encounter, close encounter. So it's just basically always doing the slow thing, plus all the overhead of checking. And there you're just better off just using the slow thing the whole time. So these hybrid integrators are really good in situations where most of the time nothing interesting happens, but it gives you a way to like catch the bad things happening and switching. Yeah. Does that help?
Yeah, thank you.
It would be fast to check if you have a close encounter, if the forces.
I mean, yeah. It's doing all sorts of fancy stuff, right? Like,
More than just this.
yeah.
Okay, sorry.
No.
Distance, but it's not so simple.
Yeah, it is tricky, right? Like in the Wisdom-Holman map, it's that like most of your Hamiltonian is the Kepler problem, and then you have this little piece. And what you have to do is when you start having close encounters, you have to have some scheme of like moving these terms that are getting bigger and bigger and like move these over into this other thing so that you have a big piece and a little piece. And all that like shifting back and forth and then solving some of it numerically, it does add significant overhead. Yeah. Yeah. See you much.
Well, I think we are past time, but I think there's still holes in your schedule.
Yeah.
So people have, I don't know if you want to say right now, but people can still sign up to try to ask individual questions.
Absolutely.
But let's make sure we all think. Yeah.
Thanks for coming.
One last question.
Yeah.
So if Planet 9 is discovered, should be in favor of destroying it, so there's still 8 and
Yeah, it'd be a big problem for WH fast by 12. Yeah,